Okay. Enduring to the end is definitely not a do-it-yourself project. It's kind of a nice thing. First, it requires the Savior's redemptive power, and second, it requires the Holy Ghost, who will both guide and sanctify us. And third, we must be an integral part of the community of saints, serving and receiving service from our brothers and sisters in the gospel. With baptism, we become part of the body of Christ, and each of us has a role to play, and each of us is important. But in order to succeed, we must be unified with our Savior. Okay. I think this is a really important thing to think about. And I chose this because today we're going to be thinking about the parts that make up sound. And that it's not just usually one frequency that's making up the sound. We're going to become really familiar with spectra today, and we're going to use them to analyze sound the whole rest of our class. Okay, so let's go ahead and start with review. So a few review questions. Okay, how can you tell if something is vibrating at a natural frequency? I'll just let you volunteer for right now, if you have any thoughts. How can you tell if something's vibrating at a natural frequency? There are two big things. Yes, please. Yep, really large amplitude, which means it's resonating. Okay, good. Anything else? Okay, yes.
It has a constant motion, like it'll never stop.
It has a repeating pattern, right? Yeah, one that keeps repeating over a certain time period. Okay, good. All right, what determines the shape of a natural mode of vibration? What determines if there are nodes on the ends or antinodes on the ends? Yes, please.
It depends on like the boundary conditions. So like if it's a string, it's like loose or fixed on the edge, or it's like a tube of air, it's like tapped or open.
Exactly. So it's the boundary conditions, whether it's fixed or free end of a string, open, closed end of a tube, that will determine what the mode shapes are that can fit the standing waves, whether they have to have nodes on both ends or antinodes on one end and nodes on the other. Okay, are there questions about that impact of the end conditions? Okay. What is the relationship between mode number and the mode's natural frequency? Anybody? Like as the mode number goes up, what could you say about the natural frequency of those modes? Yes, please.
It increases.
It increases. So mode one is always the lowest frequency. Mode one always has the lowest natural frequency. Okay, good. Okay. And then what is the relationship between the wavelength of a mode and its frequency? As the frequency is going up, what's happening to the wavelength? Going down, it's getting smaller, right? And that relationship is expressed through the speed of the wave, right? So if you know the frequency, then you can find the wavelength, or if you know the wavelength, then you can find the frequency. Okay. What wave speed are we using for all of our tubes? 340 meters per second. Yes, please.
So you said the wavelength one, as wavelength goes up.
They're inversely related. As one goes up, the other will go down. So if frequency goes up, wavelength will be shorter. But if the wavelength goes up, then the frequency will be lower. Okay. Any other questions about that? We covered a lot of stuff last week, even though we only met 2 days. So just need to make sure we're getting those ideas of waves and standing waves good in our, well placed in our heads. Any other questions about that or what we did last week? Yes, please.
Why is it that?
Okay, so her question was, why are fixed and open together? So a fixed end of a string and an open end of a tube. Okay. And it's because something is 0 at that end. There's a node of something at that end. So for the string, it's fixed, right? But for the for the string case, this is a graph of displacement versus distance. You know, when we're doing like this. And for the tube case, so for the tube case, it's the pressure as a function of distance down the tube. that is 0 at the closed ends of the tube. So it's because the quantity that we're thinking about, the displacement or the pressure, goes to 0 at those ends. Okay, and then conversely for the other one, please. Open ends, sorry. Yes, open ends, sorry. Open ends of tube have 0 pressure. Yeah, sorry, I misspoke. Thank you. And closed ends have maximum pressure. That's a weird thing to think about because we don't see that, you know, the pressure going to 0 at the open ends, but it is the case. All right. Any other questions about that before we move on? All right, so complex waves. Okay. So here is a little diagram of what we mean between the difference between simple and complex waves. Okay. So give me some words to describe the simple wave. Yes, please.
Not like a exactly repeating pattern.
So it
Sorry,
can't,
complex.
yeah, it can be a repeating pattern. It's just a complex repeating pattern. Well, we're going to show some examples of that here in just a second. Okay, good. Yes.
Sine wave.
It's a sine wave. So a simple wave is a sine wave. How many frequency components are in a simple wave? Only one. Okay, there's only one frequency component. Okay, so if you were asked to draw the spectrum of a simple wave, what would you do? Okay, so every time we draw these spectra, we're going to have amplitude on the vertical axis and frequency on the horizontal axis. Okay, and for a simple wave, there will be a single peak. Okay, so we're going to draw lines like this. When I show you the measured spectra, when you look at it, it's going to be kind of like jittery. Okay, but in our class, we're just going to draw the peaks and ignore the background noise. Okay, all right. Questions about that? There's only one frequency. What does that sound like? Sounds very much like this. Okay, and that would be an example of a simple wave. Okay, just there's not like a lot of tone color or texture. It's just one frequency. Okay, whereas opposed to if I do something like this, you can hear lots of frequencies, right? So that would be generating a complex wave. Okay. We're going to go ahead and look at, well, no, actually. Okay. Elena, can I ask you another favor? Oh, she went and did another errand. Okay. All right, so just a single frequency. Okay, so complex waves will have a lot of them. Yes, please.
What was the name of the graph?
This graph right here. Very good question. So this is a spectrum. Okay, and so what a spectrum is it basically takes, you take the sound, whatever microphone's listening or whatever, and you take that sound and then you run it through a mathematical operation or computational operation called the Fourier transform. And it divides it up into sine waves. And it tells you it's the vibration recipe, right? How we introduced it before. Okay. And it tells you that there's this much of frequency 1, and this much of frequency 2, and this much of frequency 3, things like that. Okay, so that's a spectrum. Okay, there's one other kind of picture that we're going to draw a lot, and this is the waveform. Okay, and so on this axis will be the pressure, the sound pressure, and this axis typically will be time, because your microphone's just in one spot, right? Listening over time. And that might be sinusoidal if you had a simple wave, but it might also be complex, but it could repeat that complex pattern. Okay. So that is called the waveform, and that's as a function of the pressure as a function of time. Okay. Okay. All right. So now with regards to your two screens. I want to keep these questions so I can remember them, but
What will be
oops,
your New
nope,
Year's
that's not
resolutions?
what I want. Okay, this was your learning activity, right? Once we got the correct link of their updated one, which is really nice because it used to not run on as many things. Okay, so I could not look at your answers because I can't log into Learning Suite, so we'll just have to take volunteers. Question 1, how did the value of the amplitude slider affect the contribution of the corresponding harmonics? So if you slid this up and down, somebody describe what's going on there. Okay. Yes, please. The volume increased, right? The loudness, right? If you played the sound, okay, good, good. Okay, looking at this orange line. Sorry, I'll turn the lights off so it's easier to see. Looking at this orange line, okay, you can see, so this up here, the top panel is the spectrum. It's just a discrete spectrum where there are just 11 frequencies, okay? Then this is showing the time waveform corresponding to each of those frequency partials. And then this is the sum, the superposition of all of those, or the whole time waveform. And if you zoom out, you can see that it is in fact periodic. Okay. All right. So as I change this, the amplitude that frequency is contributing, the orange line in the middle, changes, right? Gets more and more pronounced. Okay. But then if I go negative, what's going to happen to that wave? It flips, right? So if you look, let's look right here. See how there it has a positive slope going through 0, then all of a sudden it flips. See that? Okay, so that it has to do with the relative phase of the two frequencies. When we look at spectra in real life, you're going to get to look at them on your phone. I'm going to show you on the computer. We'll just be looking at the absolute value. We won't be looking at the positive or the negative. But just so you know, that's the idea of the phase. Okay, good. Oh, that was question 2. Okay. All right. Okay, so if I add more harmonics, if I add the yellow and then the greens and blues, what's going to happen to my sum there on the bottom? How can somebody describe that? Is it going to get smoother usually? No, it's going to get a little more crazy, right? And you can make it do all sorts of funky patterns and things. And so it is a very complex wave, but it is still repeating, right? So if you start here, where it goes down, and then it goes big up, and then we're going to repeat big down, juggling around, big up, and down. Okay. So this is a complex wave, but it is still periodic. How are we on that word that's periodic? Okay. All right. Other questions on this? Other things you observed? Okay. So the last question is, how many partials were you able to match on this wave game? Did anybody play the game? Anybody get to do 5? Did anybody make all 5? You got all 5? Good job. Okay, 4. You got all 5? Okay, 5 or 4. Okay, it was tricky though, right? The more complicated they are, I'll just do a 3 for right now. Well, they give me 5 choices though, right? So then you kind of start and you're like, okay, well, it's going negative out of that center. So maybe we'll do that. Yeah, it's very tricky. I'm not going to take time to do it right now, but yeah, it'll be okay. Okay, but that's the idea between simple and complex. Okay, so if I clear this, if I reset everything, okay, I'm going to take this green one down. Well, sorry, the red. So there's the red. Okay, how many? If this is as a function of space, not time, so a snapshot in time, how many wavelengths are fitting? 1. Okay, so if I now go and I instead raise this one up, how many wavelengths are fitting? 2. Okay, and how about this one? Okay, so what does that tell you? Now that you can see that relationship in frequency, what does that tell you about in wavelength, what does that tell you about the different frequencies that they're using here for these? Go ahead and say it. They're like the modes, right? They're harmonics. They're integer multiples of the fundamental. Okay, so the fundamental frequency here is that one, but then this one is 2 times that. The frequency will be 2 times because the wavelength is half as much. And in this yellow one, it's 3, you can't do that. 4, this is 4 times, so that means that the frequency would be a quarter as much, or the wavelength is a quarter as much because the frequency is 4 times higher. Yes, please.
So are these harmonics or are these inharmonics?
These are harmonic partials.
Okay.
Yep, so harmonic partials mean that all of the frequency components are multiples, whole number multiples. That's what it means when we say integer, a whole number multiple of the fundamental. So F1, 2F1, 3F1, 4F1, 5F1. Question? Yes, very good to clarify. So this example has only harmonic partials, which is why it always produces a periodic wave. Okay. So that's something you need to get in your brain, is that harmonic partials produce periodic waves. Oops. It's all the way at the bottom, I guess. All right. Okay, questions about that? About these words of partials? Oops.
You'll hear the sounds of 2 instruments build up by adding.
Okay, I'll explain it first. Okay, any questions about partials? All right, so are the ones I drew here, they're roughly integer multiples of each other. On all of, this is just a clue for your homeworks and stuff. There will be little tick marks here on the bottom. Those tick marks will always be evenly spaced. They won't necessarily have numbers, okay? But using the tick marks, you should be able to see if the higher partials are whole number multiples of that lowest one, okay? Right, so for example, where did my blue go? That was the best one. If your spectrum looks like that, what would you call that? How do you identify that wave? Simple wave, right? Has one frequency component. Okay. If it had like this, okay. This is the fundamental. It's also the first partial. Okay. So sometimes people get confused and think that it's like 0 and this is 1, but this one really is 1. This is the first partial. Okay. How would you describe this spectrum? What are some of the words you could use? How would you describe the relationship of the upper partials to the fundamental? Yes, please.
As the frequency increases, the amplitude decreases.
As the frequency increases, the amplitude decreases. That is a good observation. Okay. This also would be an example of a case where there are all harmonics, right? 2 times, 3 times, 4 times, 5 times. Okay. Or so the upper partials are all the harmonics. Okay. And if that's true, if all the partials are harmonics, then that would yield a periodic wave. But it would be complex, right? Complex periodic wave. Now, what about if I take some of these guys out? Are the upper partials all still harmonics? Yes, but we don't have all of them. We only have what? The odd numbered ones, right? 3 times, 5 times, like with the open closed tube examples that we did last Friday. So, and even if there was only that much. It would still be a multiple of this, right? 2, 3, 4, it would be 5 times the fundamental. So it would still be a harmonic partial. You would still get a periodic signal, but you may or may not. Okay. Now, so that's that case. If you have lines that are, obviously not evenly spaced, right? What do we say those partials are? Inharmonic partials, okay? And those will always form a non-periodic wave. Yes.
For it to be a harmonic, it has to be integer multiple.
Yes, to be a harmonic, it has to be an integer multiple of the fundamental, and the integer is like a whole number. So 2, 3, 4, 5, 6, any of those whole numbers, no fractions, no decimals. Good. All right, so now the demonstration that's going to be shown to show you how important this is and to answer the question as to why you can identify different instruments in the orchestra when they all play the same note. Okay, the key lies in these partials. Okay, so in this, there's going to be 10. So they've taken a sound, they've done the Fourier analysis, broken it into the components. Yes.
Could you go back over what the harmonic is?
Yes. Okay. So inharmonic partials. Okay. Are not whole number or integer multiples of the fundamental. Everything else that's not harmonic partials are inharmonic partials. Does that help? Okay, yes.
How would you signify on the spectrum if it had like a negative amplitude?
Yes.
Does it just go down like the program?
So it does not. So the program was showing you the waves, and so it was showing you the superposition, the phase of them. But the spectra that we will look at will be the magnitude squared. So they will always be positive. You can get that information out, but it's not usually visually displayed. It's in there mathematically, but not usually visually displayed. Okay. Good. Okay, other questions about that? So harmonic partials are integer multiples. So I'll just use the N to stand for an integer like we did the other day. Okay, so in this audio demonstration, they took a sound of an instrument playing a single note. They did this Fourier analysis, so they have the amplitudes of the 10 frequencies, the 10 lowest frequencies. And now they're going to play you first only the first one, then the first 2, then the first 3, then the first 4. They're going to build up the sound one frequency at a time. And you're going to see how many partials you have to identify the instrument that's playing. Okay, so that's what this audio demonstration is.
Effect of spectrum on timbre. You will hear the sounds of 2 instruments built up by adding parts.
So go ahead and count. I have to go get one adapter for my office. So how many did it take to know what that was? About 6, 5, 7, something like that, but it was a Carolyn bell. How many did it take that time? took fewer, to at least get the right category, right? But what happened? How would you describe what happened to the sound as those partials got added? Give me a description of what changed with the sound, even once you knew it was guitar. What changed as you listened, added more and more partials in?
Well, it started off like this very flat sound, and then as it kept going, it got brighter and brighter. You could kind of hear the tinginess of the guitar string. You couldn't hear that at the start.
That's very important. Lots of good words in there. Okay, so it'll sound brighter when there's more high frequencies. It'll sound warmer if there's only low frequencies. It'll also sound fuller if there are more frequencies. Okay? Twanginess or anything like that is always related to high frequencies. But so that's why everybody in the orchestra can play A440, and you can tell the difference between the trumpets and the oboes and the strings. Questions about that? Relative amplitudes of those higher partials. So on these slides, there are written out notes, or like more definitions written out. And things like that. If you would like to find them. Now I want to go ahead and look at additional spectrum. All right, so on the top, I have what's called an oscilloscope. So this oscilloscope is showing you as a function of time, the waveform. Okay. Microphone in my computer is in one spot. It's just going to show you over time what the sound is coming in. Okay. So that I'm going to be quiet. Background noise. It's auto changing over here, this axis. Okay. So that's why sometimes it's just really fuzzy and other times it's not. Got to make a loud one first. Now it's not changing on the vertical. Quiet. Background noise in the room. Okay, and then once I start talking, it's a lot more energy, right? And so if I do periodics, so let's do our sounds again here. Looks pretty sinusoidal, right? Pretty simple. I'm going to make this right. Much more complex, right? What about tuning forks? What do you think they are? Simple or complex? Simple. That's much slower. This was because I see the computer. So the background noise influences the shape that we basically have. Okay, and if you hit it quieter, it's more sinusoidal. Okay, here's another train one. Okay. So those are the difference between our simple and our complex waves. Now I should do them again with the spectrum. Here we have our FFT analyzer. Shows you the spectrum. It's a little tricky, right? trick is that we don't actually want to see a logarithmic frequency scale. We want a linear frequency scale. There we go. Big old restart. Questions? Let's go ahead and do the questions on our paper. There are definitions of partial and harmonic. And on there for us. All right. Number one, go ahead and get out your whatever. Which of the following list of frequencies in a spectrum has harmonic partials? And probably process of elimination by the ones that don't have. Answer is A. It's 24, 3 times 24, 5 times 24. 24. B is what we will call slightly inharmonic partials. Extra beating between those. There are instruments that have those, but and C would be a list of inharmonic partials. And if there are some multiples and some not multiples, then you'd say there are both harmonic and inharmonic. Questions? So answer was A. Yes, please.
Can you go over the Fourier analysis again?
The Fourier analysis is the mathematical or computational algorithm that divides a time waveform into its frequency components, into the sum of different sine waves that make up the, like you did on the learning activity. You were doing the inverse Fourier analysis. You're saying this much of this frequency makes this wave. Fourier analysis just says this wave came from this much of each of these frequencies. Okay, number 2. On the back, which statement accurately describes this graph? Have ease, which means you just turn it sideways. The answer is D. And A is false is because the first partial is the fundamental. Make sense? Questions about that? All right, and then 3. How would you describe this spectrum?
What are upper partials exactly?
Everything above the first line. First line is going to be called the fundamental and the first partial. It's called both of those things. And all of the lines above that are the upper partials. Thank you for asking.
So fundamental isn't the first harmonic.
So
It's the fundamental first partial, but like, just like on the front, I have like the question: is the fundamental the first harmonic first partial? So it would be the first partial, but not the first harmonic.
it is the first harmonic because it's 1 times the fundamental frequency. Which one is this one? Yep, so D is the correct answer. If I can get this run now. show you. I really like to show you both of these things at the same time. It's a teeny bit tricky. So again, on the top, we're gonna have the waveform, and on the bottom, we're gonna have the spectrum. These are currently auto changing. I'm not gonna mess with it right now, but I'll get a better format for next time. Okay, so I'm gonna be quiet so you can see the background noise level on the spectrum. That's just the amount of noise in the room. This is in kilohertz here on the bottom. So this being 4 kilohertz, 8, 13, 17. Okay, so now I'm going to do my noises again. So mostly one partial, right? A little quieter. Really just one peak above those lines. Okay, back. Let's do our train whistle. So those are not necessarily evenly spaced. Now I'm going to do some voice sounds for us. If I do vowels, yeah, all those partials were like nicely spaced. So voice sounds, anytime your vocal folds are vibrating, have harmonic partials. Because the motion of the vocal cord is periodic. Periodically vibrating things produce periodic have harmonic partials. Watch how those change. We'll talk all about this when we get to speech as to why the amplitudes are different, but I'll just do it. Almost monotone, right? So like the fundamental didn't change, but the relative amplitude of those harmonics are how we actually distinguish all of our speech sounds. Say any word on any pitch. Right? Relative amplitude of the partials in the spectrum, that's the big thing. Okay, now if you make noise sounds like shh, are there harmonic partials? Is there a fundamental really? That's definitely in harmonic partials, non-periodic waveform. Shh. Okay, things like that. Now, if you do the voicing and the noise, then you get some harmonic partials, lots of inharmonic partials. We'll talk all about that in speech. Questions about that? All right, number 4. Describe the key elements of complex periodic and non-periodic waves. Which of the following would result in a periodic sound wave? Cymbal crash, wind blowing through a crack in the window, a person yelling "ee," a tree falling in a deserted forest. You see a person yelling "ee." Time your vocal folds are engaged in intense voice speech sound, you will have harmonic partials. It will be a periodic wave. Which of the following would result in a sound wave with inharmonically related partials? Blowing a violin, blowing an organ pipe, blowing a tuba, or striking a bass drum. Inharmonic partials would be the bass drum. So the sounds from, and we're going to listen to each of these individually later, bowed string instruments have harmonic partials because the underlying standing waves, right, are the waves on the string. And we showed last time that they are harmonically related. F1, 2F1, 3F1. Those are the fundamentals modes of that system. Organ pipe also will have only harmonic mode because it'll be open, open. Tuba will model as open, closed, closed at the mouth, open at the other end. So we'll have harmonic partials, but only the odd ones. Remember that. Then the bass drum, it has a two-dimensional surface, and the modes, standing waves on that are actually inharmonic once you get to 2 dimensions. So it's only these things that can be considered one-dimensional systems that have. Okay. All right, so take a minute and try to fill out this chart. Write a word or two that will help you know periodic and non-periodic. What would that look like in the waveform in the time domain and in the frequency spectrum, the spectrum in the frequency domain? How would you, from a waveform or from a spectrum, say this is a periodic or a non-periodic? Or quasi-periodic, which is talk to your neighbors. Go ahead and take 2 minutes on this, and then we will.
I understand. To be drawing this, we don't know. We're asking our kids. No. Oh no, this is like.
I have one of it.
Wasn't for you, sorry. I'm just getting my settings. You're right. Let's go ahead and come back now. Periodic waves. Somebody tell me, how does it look in the time domain? Please. Some time period T. What would it look like in the frequency domain, a periodic wave? Describe it. Spaced. Spaced partials, harmonic partials. All right, non-periodic wave then does not repeat and would have inharmonic partials. Quasi-periodic would, the general pattern would repeat, but it has some extra noise in it. Okay. So let me try to show you. Oh, we got a little better. See, like the general pattern repeats, but the individual noise doesn't, because there's some harmonic partials that have a lot of energy, but then there's a lot of noise. Or it can be slightly inharmonic, where you would get beats. Like this B on the front page. This B on the front page would be an example of a spectrum that is quasi-periodic. A is an example where it is periodic. B is an example where it is. You may have to write A as multiples of 24 to see it more clearly. Help you get a foundation on these words. We're going to use this throughout our class. In a couple more learning activities, we're actually going to download a spectrum analyzer on your phone. It's all a free raise, but then you there you go. It will help you get able to upload. This one.